Everything we talked about in Chapter 10 were initial value differential equations, where you had all of the initial states necessary to define the origination of the problem and project it out into time or space or whatever dimension of interest you had. I guess time and space are typically both associated with an engineering differential equation. Chapter 11 deals with boundary value problems where you may not necessarily know every initial condition needed to predict the future. There are different ways that you might be delivered the boundary conditions. In this case, a problem statement related to the second order of a derivative, a second order boundary value problem. There are two distinctly named boundary condition types that, well, really just kind of make you sound smart if you know how to properly refer to them. If both of the boundary conditions are given to you as positions, perhaps, or state values, basically the zeroth derivative terms, you can call those a Dirichlet boundary condition. An example of this would be like if they give you the temperature at both ends of a bar that you're looking to find the heat transfer through, or a fin. If they gave you the fin temperature at both ends, just simply called Dirichlet boundary conditions, and that's two states, two positions, two values at the end, usually the endpoint locations, the boundary points. If the values are given to you as two derivatives, so the slope of these elements is known at the boundaries, that's called a Neumann boundary condition. So the slope being constant, there still should only be a particular set, a unique set of points on the boundary that would result in those slopes. Perhaps some differential equations could be found where there'd be a multitude of solutions that could correspond to those slopes, but for the most part, it'll be a unique solution, and you're looking to find the corresponding and as of yet unknown point boundary conditions such that the differential equation is satisfied throughout the interior and simultaneously satisfies all of the boundary conditions. In the process of seeking all that, you'll find many real solutions that don't match your desired boundary conditions, and it's only when everything lines up that you'll actually be satisfied throughout. So the third possibility is just really called mixed. You have a mixture of derivative-based and position-based. Actually, I think both of these, each boundary condition is mixed. So derivative and position of each is the boundary condition, but you might also be provided the left-hand side derivative, but the right-hand side position. You'd have mixed boundary conditions across the domain. Not everything has to be linear. There's possibility of nonlinear boundary conditions and many different aspects that could be delivered to you. Like in this example, structural beam bending, going straight through the textbook. There is the governing differential equation for the setup, and the boundary conditions are given to you quite explicitly. Since they are anchored at both ends, the slope at both ends is known to be 0, both at x equals 0 and x equals L. Since it's anchored at both ends, we also know that the position at both ends until something breaks, which isn't modeled by mathematics, is given as 0. So that would be fairly straightforward. You would just be solving the curvature and deformation of the beam throughout the middle point. There are two distinct methods the book covers to solve these boundary value problems: shooting method and finite difference method. The shooting method involves guessing at the initial condition, solving the entire system, basically having the computer do it, you wouldn't do it by hand, and then seeing what the other boundary condition turns out to be. If the other boundary condition matches what you want it to be, you're done. If not, make a better guess. And by make a better guess, I mean use the numeric methods we taught you in Chapter 3, namely secant method, bisection, linear interpolation, some numeric, I won't say optimization, but some numeric zero finding tool to take the error between your projected solution boundary condition and the desired solution boundary condition and move that difference down to 0. If you want to do something in a more direct solution method, especially if it's linear, you can use the finite difference differential equation solution method. This is very, very useful if you are going to be able to write distinct finite difference equations for every interior point, especially if it's a linear relationship between points after they've been discretized, because then you can put it into matrix form and use any number of the matrix solution methods we've taught in the class, or you might have available otherwise, to find the answer to every single state simultaneously. It gets rid of iteration, it gets rid of searching, you should be able to go through and solve the problem more or less once to find the answer. But first, let's discuss the shooting method. The name is very apt. It describes exactly what's going on. If you take a shot on the left-hand side boundary condition and the slope is too low, then you might impact the other opposite side boundary condition below where you cared to arrive. If you take a shot on the left-hand side and its slope is too high, then you might impact the right-hand boundary condition above where you decided to arrive. And really graphically, if I can reference a plot that's coming up, you would take this prime guess, your W prime L, W prime H, high and low guesses, take their resulting Y values they resulted in for the boundary conditions on the other side, and then linearly interpolate between those 2 points to figure out what initialization, what W slope initial would result in exactly matching the boundary condition you desire. So whether it's linear interpolation or whether it's some sort of successive approximation or just a brute force search, you raise the angle 1 degree every time, fire again, and eventually something gets close enough. You can take whatever method you want numerically to find the actual solution to the differential equation that satisfies all of your boundary conditions. Of course, some tolerance criteria has to be employed. You shouldn't expect to get an exact, to the 20th decimal place answer match, but if you need it accurate to a 1,000th or a 10,000th or whatever the case may be, you can employ that convergence criterion just like we would in zero finding, just like we did for any sort of other iterative methods we've gone through. So that is the core of shooting method. The other method worth discussing is called the finite difference method. This is for, how should I put it, systems which are easily discretized in space. This is for systems that are either linear or nonlinear. In fact, it's fairly straightforward to discretize a differential equation, more or less any order, into a number of points using the techniques we developed, I believe, in Chapter 8, the differentiation chapter. Namely, these definitions seen right down here. Anytime you would see the first derivative, perhaps dy dx, or the second derivative, dy dx squared, expressed in a differential equation, you can now take discrete points. Once you've split the domain between the left-hand side and the right-hand side into a series of points you are tracking, you can take that series of points and define the derivatives between them. This being the central difference second derivative, the central difference first derivative, both of which are dependent on the adjacent points of your point of interest. So if you're looking at point, what is this, x of I, the central difference actually depends on the left point and the right point of equidistant h around point x of I. So it's a fairly straightforward process. If you have some example differential equations given in 1124, you have the second derivative of y with respect to x plus some function of x, unknown function in this example, multiplied by the first derivative plus a function of x multiplied by y equals some forcing function h of x. To get this into a discretized form, all you really do is you substitute in the discrete forms of these derivatives. So if you notice, the second derivative becomes here the central difference second derivative definition. The first derivative is central difference first derivative definition, and everything else is really just numbers. You would be given the function of x here, you'd be given g of x, you'd be given h of x in a real problem, leaving just your unknown variables y of I plus 1, y of I minus 1. So the entirety of this differential equation is reduced to three unknowns. The previous, the step you're on, and the future step values of y of I, which have discrete values because, well, you discretize the problem. Looking at an example of this, practical example that's quite easy to follow, and hopefully my comment will add some merit beyond simply what the book would tell you. The second derivative of temperature with respect to space on this small pin fin equals a collection of coefficients corresponding to the physics of the problem, where in this case h is a convection coefficient, p is the perimeter of the rod, k is a conduction coefficient, and ac is the area of the fin. That's then multiplied by temperature of that point minus the surface temperature. All equals 0. Valid in the region 0 to L, where L is the length of the rod. And so they go through and just immediately do two things. The first of which is substitute in the central difference formula for the second derivative of temperature with respect to x. So you can just quite literally read that right out of Chapter 8. throw it in there. They substitute the term beta in for this collection of coefficients in front of the temperature difference, and they set the temperature difference into discrete notation. So temperature at I minus T of S, which T of S is, according to the problem, a constant. This makes things fairly straightforward to solve given everything else you know from the textbook so far from the class. The important thing to realize is that when they discretize this into 6 different points, point number 1 and point number 6 are known. Those are the boundary conditions. They told you what the temperature was on the left-hand side. It looks like to be 473 Kelvin. They told you the temperature on the right-hand side, 293 Kelvin. It's only the interior points you have to solve for. So to get a reasonable idea of the curvature of this function, to get a shape of the temperature curve throughout, you just need to solve for the 4 unknowns in the 4 equations describing the interior points. You might guess that those highlighted equations add below are exactly that. At point 2, you take the left-hand adjacent temperature, noticing that they've rearranged the differential equation so that each coefficient is associated right with its own variable. So there's the coefficient for T2, and T3 coefficient is just 1. This all equals a set of constants, which could all be multiplied together to get rid of the alphabet soup there. And those set of constants essentially become the right-hand side solution vector of the matrix form. Because the same thing happens for I equals 3, I equals 4, I equals 5. And in those cases, you are able to represent everything in matrix form. Notice one thing that's unique about I equals 2 and I equals 5 is that they reference, in the case of the second position, it's dependent on the point just left of it. So it references T1. T1 is known. So if you look down here in the solution, they've moved T1 over to the right-hand side because it's not a variable. It is not in the list here as an unknown. T1 as a boundary condition is given to us, so don't create a problem for yourself and put another variable in here that's only referenced in one place and you already know the value of. Just move over to the right-hand side. It's part of the solution because everything over here just gets calculated down to a number. Same story for I equals 5. At the 5th point, you're dependent on the point just to the left and just the point just to the right. So as you know T6, throw it in the solution vector. You don't have to have another independent variable to solve for something you already know. Save yourself the complexity, and the problem is more or less set up. Notice that it ends up in tri-diagonal form. Many of these single variable differential equations end up in that way. They're only dependent on the items just to the left and just to the right. And this is a perfect method for using the Thomas solution method, the simplified Gauss-Jordan for tri-diagonal matrices solution method, to accelerate solution. In this small problem, in this simple form, that's going to save you about 2 milliseconds of solution time for the maybe 30 minutes to an hour it takes you to program in the Thomas method. But in large problems, it seriously does take the number of calculations down by orders of magnitude and saves a lot of time. So the final answer that results is just really a series of points. Everything comes out in balance, and if you've done all the things right and not messed up a negative sign somewhere, then they come out in kind and nice alignment in an arrangement that satisfies the discrete needs of the differential equation. Boundary conditions are easy to satisfy because they don't move. The boundary condition is what it is. The temperature there is going to be exactly what the book says. The important part is that the derivatives and the relationships between the different orders of derivatives making up the differential equation in between are correct. So this curvature satisfies all the heat transfer equations, satisfies convection equations of heat leaving, and you're set to go. But now time for a complication. Same problem, except convection and radiation are included. You're like, okay, no big deal. Convection, we kind of handled that. It was a second derivative, we had that last time. There's convection, we had that last time. There's radiation, we had that. Oh gosh, temperature to the 4th. Yeah, that's it. That's the complication. Everything else just had temperature to the 1st. Wasn't a big deal. That's linear. Even the second derivative here just referenced some adjoining temperature locations. It didn't necessarily require us to have things at a higher power, but temperature to the 4th, that's nonlinear. So, whenever you put this matrix, whenever you do the rearrangement, if you try to separate this out into coefficients, the closest you get, after going through all these subdivisions for I equals 2, I equals 3, 4, 5, same type of arrangement we did in the previous problem. They have the endpoints on the right, endpoint on the left. Those are known, thank goodness. there's a formulation you get down below, quite similar in the coefficient matrix, quite similar in the list of unknowns. The answer is close, but they have this entire extra array of nonlinear terms. So you can't use Gauss-Jordan directly. You can't use any of the linear inversion and multiply methods because it's a nonlinear equation. The temperature to the fourth, so T2 to the fourth, T3 to the fourth, T4 to the fourth, etc., takes that luxury away from us. Surface temperature to the fourth, fine. It's constant. That's not an actual variable. It's known. These are the nonlinear coefficients making life more challenging. So the solution method here is you have to use the iterative solution. You have to solve essentially for the unknown value t and then just iterate through and hope it stabilizes. If you need to numerically dissipate some of the instability away, please do that. Relax the problem numerically by only taking a certain percentage of the indicated step. If the next iteration says you should increase T2 by 400, relaxation of 30% means that you only take 30% of that 400 step. And that can massively help to relax, to stabilize a numeric system. So this defaults back to iterative solution methods for nonlinear equations. You can't use, in fact, there's very little incentive to put it into a matrix form here. You might as well just take these equations above, solve them for the individual t variables, find an arrangement or a level of relaxation that makes it stable, and enjoy your solution. The answer comes out not all that different. There's the answer down there bottom right. As you might remember, the previous example kind of looks a lot the same. Boundary conditions, I believe, are similar. The differential equation solution throughout is about the same. One reason for this is that without a large temperature difference between the surface temperature and the temperature of the bar, your actual radiated energy stays very, very, very low. Radiation heat transfer only really becomes significant at very high temperature. Whenever you have, hundreds, if not 1,000 degree difference between you and surrounding materials, the difference between emission and absorption will not be all that significant. So that's part of the reason. The other part is that, well, that is the reason. These other terms dominate, is what we're saying. So this has one distinct implication in engineering education that a lot of students have seen but not yet understood maybe why. Finite element solutions in many common CAD programs. I know in SolidWorks, whenever you are pursuing a solution for small displacements, small deviations, small deflections, SolidWorks is able, or I should say in general, FEA solution methods are able to keep things linear. So you stay in the linear elastic region of the material model. So solving it in a linear elastic form allows you to use matrix inversion and directly solve for the unknowns. That's why those linear FEA problems are very fast in solution. Even if they have many, many points, they more or less just invert the matrix, solve, or they use who knows what matrix solution method is behind the scenes in those actual codes, but they find a direct solution of the matrix and present it. If you go beyond the linear region of a material due to excessive strain at any point, even if it's just one point in the entire domain of finite element solution, you'll oftentimes be asked, do you want to employ the nonlinear iterative solution method? And that's exactly why. You've taken the solution methodology away from the quick invert, multiply, or otherwise quick matrix solution methods, and now you've gone to an iterative nonlinear equation where they have to use their nonlinear models for materials in combination with the equations using that same data. So that is why you get the massive increase in time and the requirement to iterate the solution for finite element calculations. So it's just nice to see that even though these examples in the textbook are on very simple, low order, low point count problems, that this behavior, the ideas that you're learning here in this textbook, are directly applicable to the highest end of topics in engineering.